Welcome back, and let's start talking about continuous random variables. We've talked about discrete random variables and how we calculate probabilities for discrete random variables with probability mass functions. For continuous random variables, we calculate probabilities using a probability density function, or a PDF. Now, it's usually not difficult to tell the difference between a continuous and a discrete random variable. If we're counting the number of cars in the parking lot, counting the number of students enrolled in a class, if we're counting, that is almost always going to be a discrete random variable. But if we're measuring something, height, weight, that's almost always going to be a continuous random variable. And I'm saying almost always, not that I'm thinking of any case where it isn't. It's just that if I give absolutes, somebody always finds a way to contradict. So I can't think of any exceptions to measurements, continuous random variables, but there may be one out there somewhere. All right, and then here's an example, and it's the example your author starts out with in your textbook, but I kind of like it. So suppose that we've got a strip of highway, and it's 200 units long, kilometers, miles, and we're interested in where accidents happen along this highway. Now, let's think about an interval along this highway from A to B, and we're going to make the assumption that the probability of an accident between mile markers A and B, maybe I should write a little IN in here, NAB, is dependent only on the length B minus A. So if we're talking about a long strip of highway, then the probability that an accident occurs somewhere in that strip is pretty good. If we're talking about a short strip, the probability would no doubt be smaller. If we use that definition and assumption, the probability that we're going to have an accident in the interval AB, and I want to adopt this notation for the probability we have an accident in AB, I'm just not going to write all those words out, would be B minus A over the length of the highway, 200, using our assumptions in the classical definition of probability. Then if this is going to be our method of operation, we've got a probability function because, number one, the probability for any interval AB is going to be greater than or equal to 0. It's going to be B minus A, and another understanding here is A would be to the left of B, so B minus A would be positive over 200. That would be positive, and the probability B minus A by this definition would be positive. And 2, the probability of the whole sample space would be 1, because the probability of the sample space would be 200 over 200 would be 1. And 3, if we take disjoint intervals, so here's our 0 and here's our 200, and if we take disjoint intervals, AB and CD, then the probability of an accident in AB or is union CD would be equal to B minus A, it's the length of the interval, or the combination of intervals, plus D minus C over 200. And of course, by the laws of algebra, that's B minus A over 200 plus C minus D over 200. And so that's equal to P of A, B plus P of C, D. So 1, 2, and 3, this is a probability function if it's defined in these terms. We want to note that we can calculate probability for any collection here of unions or intersections of intervals. If the intervals overlap, then axiom or postulate 3 doesn't help us. But if they overlap, we can write them like this. If this is an interval A, and this is an interval B, that can be expressed as A without B union A intersect B union B without A. And these would all be disjoint. So we're just saying that I could express this as this little piece union this little piece union this little piece. Now it's possible to make up exotic sets that will not satisfy the axioms and that you can't find the probability of. And I want to refer you at least briefly to paragraph 2 on page 83 of your text. You read that once or twice. It just says that in probability theory, as a branch of abstract mathematics called measure theory, it is possible that there can be subsets that we cannot assign probability to. But in this course, and in any course in applied statistics, we're going to avoid those esoteric pathological sets and just talk about unions and intersections and combinations of unions and intersections. So we're not going to have to worry about that, but we do, I think, owe it to ourselves to know that not every subset of the sample space is an event. An event is something you can assign probability to. So, okay, let's keep moving. I keep trying to get these videos short, and I'm never successful anymore. So, how do we calculate probabilities for a continuous random variable? For a continuous random variable, we use a PDF to calculate probabilities. And a PDF is a function that satisfies f of x is greater than or equal to 0 for all x in the domain, and 2, the integral over the domain x, f of x, is equal to 1, and 3, the probability that a is less than x is less than b is equal to the integral from a to b f of x dx. If a function satisfies these conditions, then it's a probability function for the random variable x that we've inserted down here. It would follow immediately, and worth noting, that for a continuous random variable, the probability that a is less than x is less than b is going to be exactly the same as the probability that a is less than or equal to x less than or equal to b is going to be identically equal to, and there are other ways that you can, you could say a less than or equal to x less than b, and one other way to say that. They're all exactly the same because the integral would be exactly the same. Another consequence of that is that for a continuous random variable, the probability that x is equal to any single value a is equal to 0 because the probability x equal a would be equal to the integral from a to a, not a to b, a to a, f of x dx, which would be equal to 0. So those are things that are not true for discrete random variables, but we learn they are true for continuous random variables. Now let's get on some examples here. Let's go to page 89 and look at example 3.18. And we're going to change colors here because I don't want to get bored with any particular color. So here in this problem, you can read the problem in your textbook. We want to show that f of x equal 3x squared, 0 less than x less than 1, is a probability density function. So we've got to show that f of x is greater than or equal to 0 for all x. Well, look at the definition of f of x. The domain here is x between 0 and 1. We're going to take an x and square it, and so that's going to be positive. And then we're going to multiply by 3. So there's no way that could be negative. In fact, it can't even be 0 because the domain is from 0 to 1. But all we have to do is to assure ourselves that f of x will be positive. I can see it will be positive. And then number 2, we have to show that the integral from, now it's over the whole domain here, so it would be 0 to x f of x dx. I have to show that that's equal to 1. Well, this would be the integral from 0 to 1. Made a mistake here. I don't have any of you in the room with me to correct me when I make these mistakes, and so I've got to be my own editor, and that's not ever a good thing. 0 to 1, 3x squared dx would be equal to 3x cubed over 3 between 0 and 1. The 3's cancel out. 1 cubed is equal to 1, and 0 cubed is 0, so it's 1 minus 0 is 1. So that is a PDF. And there's a part B to this example, so that was part A. Get a little more paper here. There's a part B that says sketch the function show the probability that 0.1 is less than x is less than 0.5, and calculate that probability. So here's all that they want us to look at. This function is 3x squared, so it's 0. That would be 0 squared times 3 would be 0. And you can sketch it better than that if you need to or want to, but it's going to look something like that. So there's f of x. Now between 0.1 and 0.5, there would be an area of that shaded region. So this shaded region, the area of the shaded, is the probability that 0.1 is less than x is less than 0.5. And as far as calculating the value, that value would be equal to the integral from 0.1 to 0.5, 3x squared dx, that is the probability density function, is equal to x cubed. We did this just a minute ago. Remember, the 3's cancel out. Between 0.1 and 0.5 is equal to, and it's calculator time, 0.124. So that's the probability. Let's do another problem. Oh, we need new paper. I'm just going to take a chance that we're not going to need anything that I've written so far, and I'm going to clear this and go back to the top. That is the top. And let's look at problem 3.19, which says same directions. Show f of x equal e to the minus x, 0 less than x less than infinity, is a PDF. All right, well then what we have to show is 1, f of x is greater than or equal to 0 for all x. Well, f of x is e to the minus x. And what does the graph of e to the minus x look like? The graph of e to the minus x looks like that, doesn't it? And where does it cross here? Well, when x is 0, this would be e to the 0. E to the 0 was 1. So it crosses at 1. And approaches asymptotically approaches 0. So it never gets into the negative numbers. So 1 is okay, 1 is satisfied. And 2, I have to show that the integral over the domain, so the domain here is 0 to infinity, f of x dx is equal to 1. So this is an improper integral and would be evaluated as the limit as r goes to infinity, integral from 0 to r f of x dx would be equal to the limit as r goes to infinity. I guess I've got to write this down again. 0 to r e to the minus x dx would be equal to the limit as r goes to infinity. Review your calculus here. This is an integration by substitution that I'm going to do in my head, but if it was e to the minus x minus dx, that would be an e to the u du. And so I want to put a minus on the dx, and to put a minus on the dx, to put a minus there, I put a minus out there to balance our universe. And then the integral now would be, this is the minus that we've got outside, but here I'd have just e to the u du, so the integral would be e to the u, and u is a minus x, like that, between 0 and r, and that's equal to the limit r to infinity. And I'm going to do something that I like to do, you don't have to do, but it's a theorem from your calculus, that I can change this minus to a plus if I reverse the limits on the integration. And so it would be an e to the minus x r to 0 would be equal to, now I'll put the 0 in, you get e to the 0 is 1 minus the limit as r goes to infinity, and you put the r in, you get e to the minus r, which is 1 over e to the r, and I see that as r grows to infinity, this is going to get, that's not very clear, this is going to get huge in the denominator, so the 1 over something getting bigger and bigger and bigger is going to 0, and so this is equal to just the 1, and this thing is going to go to 0. So we've got a PDF. Now we're asked to calculate things like, using that PDF, what's the probability that x is greater than 1? Well, on the sketch, that would look like x greater than 1. If this was 1, then this area all the way to infinity would be the probability that x is greater than 1. And we could calculate that as an integral of the improper. It's a let's see, that's improper integral of the first kind, I believe. But we also know that the law of complements work for all probability measures. So this probability would be the same as 1 minus the probability that x is less than or equal to 1, would be 1 minus, what's the probability x is less than or equal to 1? It's the integral from 0 to 1, e to the minus x, sticking in the PDF here, dx would be equal to 1 minus, evaluate the integral, would be minus e to the minus x. 0 to 1 would be equal to 1 minus, I'll use the brackets again, e to the minus x. 1 to 0 would be equal to, I guess I need to put that there again, 1 minus 1 minus e to the minus 1 would be equal to, okay, now we can just finish this up. It's going to be 1 minus 1 plus e to the minus 1 is 1 upon e. For reference only, that's exact, and this is approximate 0.3679, because e is a transcendental number. It's got a non-terminating, it's irrational as well as transcendental non-terminating decimal, and I'm estimating here to just a few decimal positions. All right, well, we're here to work problems, and so let's work another problem. 3.34. Find the distribution function for the above. Now, we haven't talked about that for continuous random variables yet, but we've got the PDF, which is lowercase f of x in the above problem. But the distribution function is the cumulative. That is, what this means is the cumulative distribution. And by convention, we let that be uppercase f of x, and that would be the integral. Now, we could say negative infinity here to x f of t dt. But remember that our f in this problem is defined on 0 to infinity, just the positive numbers, 0 to infinity. So this function would be 0 from negative infinity to 0, and so it would have a 0 integral. So this would be exactly the same as integrating just from 0 to x f of t dt. And I'm using this x as the upper limit of integration, so I've inserted a dummy variable here, t dt, to avoid confusion. And this would be equal to the integral from 0 to x e to the minus t dt, which would be negative e to the minus t 0 to x equals, I just find I make less mistakes if I change this negative and reverse these. You don't have to do that. E to the minus t x and 0, like that. I've reversed these two limits, is equal to 1. E to the minus 0 is e to the 0 is 1 minus e to the minus x. So that the what we call the distribution function, or the cumulative distribution function, f of x is, in this example, 1 minus e to the minus x. And what is that? F, uppercase F, of course, of x is equal to the probability that x is less than or equal to the x that was in the parentheses there, same x. So let's use this distribution function to calculate the probability that x is less than or equal to 5 and the probability that x is greater than 8. So super easy here at first. The probability that x is less than or equal to 5 is equal to capital F of 5 is equal to, now we remember the definition of capital F. Well, if we've forgotten, it's not very far away. There it is. So this would be 1 minus e to the negative 5 would be equal to, is equal to 0.9933. And look at problem 3.34, which says that f of y, they're giving us a distribution function, not a density function, a distribution function, is equal to 1 minus 9 over y squared if y is greater than 3 and equal to 0 otherwise. So I got a two-part definition for the distribution function f of y. Now my directions are to find f of y, lowercase f of y, the PDF, and then we'll use both to find probability y, that's uppercase y, the random variable, say less than or equal to, oh, I don't know, just say 4. That'll be a good one. So how do we find f of y? That seems like it might be rather daunting, but it's not really. So what we have to do is say, okay, f of y, what is f of y? Uppercase F now, the distribution function, by definition, would be the integral from 3 to y, PDF, lowercase f, t dt. And so the derivative of f of y dy would be equal to f of y. Fundamental theorem of calculus. All right, so then where is that taking us? Well, the derivative of f of y dy would be equal to the derivative of 1 minus 9 y squared dy would be equal to the derivative of 1 is 0. The derivative of f of y would be the derivative of 1 minus 9. Let's write that y to the negative 2 dy. Now the derivative of a difference is the difference of the derivative, so this is the derivative of 1, a constant, that's going to be 0, and the derivative of this piece is going to be negative 9, negative 2, y to the negative 3 is equal to 18 over y cubed. So that tells me that this would be f of y, my PDF, and this would be for y greater than 3. All right, so now let's do these computations that we were asked to do. We wanted to find the probability that x is less than or equal to 4, I think is what I said. So one way to do this would be to realize this is the distribution function evaluated at 4. So the distribution function, I'm sure you remember it, but here it is. So the distribution function evaluated at 4 would be 1 minus 9 over 4 squared. Y squared would be 9 over 16 would be equal to 16 minus 9 over 16 would be equal to 5 over 16. Now there's a second way that we're requested by the problem to calculate this. It's also the case that the probability that x is less than or equal to 4 would be equal to the integral from 3 to 4 lowercase f of x dx. You know, somewhere in here I switched from x to y. I'm sorry about that. I hope you're not confused by that. And this is f of y, or f of x. And so what are we going to have here? We're going to have the integral from 3 to 4, 18. I'm going to stick with x since I've got an x here. X cubed dx would be integral, I know don't have to do it this way, x to the negative 3 dx would be 18 x to the, what are we going to do? We're going to increase the exponent by 1, so that's going to give me a negative 2, divide by the new exponent, negative 2, and this was between 3 and 4, so this would be 3 to 4 is equal to, this is going to be negative 9, so I'm going to have negative 9 x to the negative 2, 3, 4 is 9, x to the negative 2, 4, 3 is 9 over 9, 3 squared, minus 9 over 16 is equal to 1 minus 9 over 16 is equal to, is that familiar? 1 minus 9 over 16 is 5 over 16. And of course, what do we got there? Exactly the same answers. All right, so this is again much longer than what I intended. I'm going to post problems, and I'm going to post them in Eraser, homework area, and so take a look. Have a good day, and thank you.